Good afternoon, everyone. This is the ninth session of ATAL FDP on emerging low power devices and advanced material processing. The session expert Dr. Bhaskar Avadia is available here, so I would like to invite him to proceed this session.
Very good afternoon to all of you, all the participants. And first of all, I would like to thank Bansal Institute of Science and Technology, Bhopal, for inviting me for this ATAL FDP. And today, my talk would be the continuation of what I had discussed yesterday in my talk number 1, and some part of it I have explained in the lab session which I took yesterday evening. So today's title of my presentation is, just a second. So today's title of my presentation is Insight into Non-Hysteretic Negative Capacitance Field Effect Transistor. So these are the contents of my presentation. First, I'll go through the introduction, then motivation behind the work, then we'll look into the literature, what has been done. Then we'll discuss about unstable ferroelectric capacitance, which I had discussed some part in my earlier talk also. Then we'll go for the Gummel symmetry test. Then there is effect of ferroelectric thickness, Dibble, negative differential resistance, backgate biasing, NC-FET based resistive load inverter, conclusion, future scope, and the references. So let's start today's presentation with the introduction. So the power dissipation has mainly two components. One is dynamic power dissipation and other is static power dissipation. And all across the globe, the researchers are trying to reduce the power dissipation. So power dissipation, like dynamic power dissipation, is directly proportional to VDD, the supply. And it is actually directly proportional to square times. So there I have written P dynamic equals proportional to VDD square. So if we are able to reduce the supply voltage, the dynamic power dissipation reduces drastically. But slide has changed, just a minute. But when we reduce the dynamic power dissipation, there is a decrement in on current and the speed of transistor. Now, what happens in order to maintain, now because the on current is getting suffered, so now in order to maintain the sufficient on speed, we need to lower the threshold voltage. As per the expression, I1 is directly proportional to VDD minus VT to the power of alpha, which is in range of 1 and 2. Now, in order to maintain the on speed of the transistor or the speed of transistor, on current or speed of transistor, we need to reduce the threshold voltage. Now, next step would be to lower the threshold voltage. Now, lowering threshold voltage would create a problem of increase in off current, because off current is proportional to 10 to the power minus Vt by S, where S is the subthreshold sweep. Hence, what it suggests, when we are going for reduction in threshold voltage, there is an increase in static power dissipation. So now we started with reducing the dynamic power dissipation by lowering the supply. But when we are lowering the supply, what is happening? The on current is getting suffered. Now, in order to enhance the on speed, what I need to do? I need to lower the threshold voltage. Now, when we are lowering the threshold voltage, what is happening? The static power dissipation is increasing. So it's like trade-off. So we started with decrement in dynamic power dissipation, but in turn what I'm getting? the static power dissipation is increasing. So this is a contradictory requirement which exists between performance and power dissipation. However, there exists one way to mitigate this problem, that is by lowering the subthreshold swing of the device. So what can I say? The reduction in subthreshold swing allows us to scale VDD and VT simultaneously, where VDD is the supply voltage and threshold voltage, VT is the threshold voltage. Reduction in SS will allow me to scale supply voltage as well as threshold without sacrifice in performance and power. So this is my next slide. So here on x-axis I am having gate length, and on the y-axis I am having the normalized power. So as the gate length is reduced, as we are going ahead in time, we are trying to scale the size of our MOSFET. So what is happening over here is the static power dissipation is starting to dominate over dynamic power dissipation. So as you can see, up to this channel length, the static power, the dynamic power was higher. Now here what has happened? The static power dissipation has started dominating over the static power dissipation. So this is what I have written. As we are shrinking down the channel length, static power dissipation starts dominating over the dynamic power, which is basically due to poor control of gate over the channel.
So ऊपर वो year है time lapse 90
Yeah.
90 95.
Yes, correct. And
टाइम के साथ मतलब year wise कैसे vary हो रहा है?
no, in order to have the closed compact devices, what we are doing, we are trying to scale the channel length of the MOSFET. Channel length means separation between drain and source, because it will give us the compact device.
Okay.
So year by year, what we are doing, we are reducing the size. Like long back when we had computers, the computer was used to be size of this room.
तो power
But now what we are doing, we are continuously scaling the size of MOSFET in order to have better performance and compact devices. So this trend is still continuing. So at present, if you see, we are if you see some mobile phones are which we are having in our pockets also, they are having 3 nanometer processor or 5 nanometer processor. So we have gone up to 3 nanometer, 5 nanometer, 7 nanometer. So this trend is only up to 2020. So that will gradually
अभी और आगे जाकर
this trend will continue. The static power dissipation is dominating over the dynamic power dissipation, and which is
और reduce होगा.
there is a trade-off.
Okay.
Previously, what was happening? Dynamic was dominating factor, and static was not much dominating. But because we are continuously increasing the size, decreasing the size, what has happened? The static power started dominating over dynamic. So we need a mechanism to control the static power dissipation, and this is primarily because of poor control of gate over the channel. So which I will be discussing in the next slide. So these are the structures which have come to make sure that the control over the channel is proper. So there is SOI, double gate structures are available, tri-gate structures are available, FinFET gate structures are available, pi gate is there, omega gate, FET is there, and gate all around is there. So all these structures, what they do, they provide a better control over the channel. So when they provide better control over the channel, so the static power improves a little. But any of these structures which I have discussed over here, none of them, they do not scale subthreshold swing. Subthreshold swing is still 60 millivolt per decade. So these structures could not scale the subthreshold swing, and which was 60 millivolt per decade for the conventional MOSFET. So now, what is actually subthreshold swing? This I had discussed in my previous talk also, subthreshold swing. So subthreshold swing is basically a combination of two factors. It's actually variation in gate voltage with respect to variation in log of drain current. So this I have expressed here as del Vg by del phi s. Phi s is the surface potential into del phi s by del log Id. So if I solve this equation, the M comes out to be 1 plus C depletion by C oxide, and N comes out to be 2.3 kT by Q. So subthreshold slope can be written as 2.3 kT by Q into 1 plus C depletion by C oxide. Now, where K is the Boltzmann constant, T is the temperature, and Q is the electronic charge. So what happens if I try to put these values, Boltzmann constant, temperature and charge, in that particular equation, it comes out to be around 59.9. So approximately I have taken it as 60 millivolt per decade. Now, so this term is 60 millivolt per decade. Now please remember, there is 1 plus C depletion upon C ox. So obviously 1 plus something is obviously going to be greater than 1. So 60 multiplied by something greater than 1 will be more than 60. So subthreshold slope in the conventional MOSFET cannot be scaled below 60 millivolt per decade. So this is what I am trying to explain. The minimum value of subthreshold swing can be 60 millivolt per decade. Now, we need to develop a mechanism through which we can reduce the subthreshold swing of the device. So, as I told, the subthreshold swing is a combination of two factors. One is the body factor and another is the transport factor. Now, that will come in the next slide. So let me just move to slide number 2. And before that, this, as I told, the conventional MOSFET minimum value of SS at room temperature is 60 millivolt per decade if Cox equals to infinity. If I put Cox equals to infinity in this equation, this term will be 0 and this will be 1. So 1 into 60 is obviously 60 millivolt per decade. The inability to reduce SS below the Boltzmann tyranny, the 60 millivolt per decade term is known as Boltzmann tyranny, is an important and enduring challenge among the researchers, among the research community. So how we can reduce this subthreshold swing? So, but before going for how we can reduce the subthreshold swing, we will look what is an ideal switch. So let me just see, this is an ideal switch and I have taken a small swing switch also. So you can see this characteristic. There is on y-axis I am having log ID, on x-axis I am having gate voltage. And this characteristic, if you are able to see this, I think brown color characteristic. So an ideal switch is a switch which has two states. Obviously two states should be there in a switch. One is the on state and other is the off state. Like our mechanical switches also, it has two states, one is off, one is on. So what should be the characteristic in on state? In on state, current should flow, and in off state, no current should flow. So the ideal value of on current should be as high as possible. The ideal value of off current should be as low as possible. So this is what the ideal characteristics looks like. And it should turn on very fast. So here we can see even Vg equals to 0 or Vg should be very less, and then it has on. It has jumped from off state to on state. Now, we all know that there is nothing ideal in this world. We have to go for real application or practical application. So designing an ideal switch is unrealistic. So we have to go for a switch which has small swing. And after the ideal characteristic, I'll go to the MOSFET characteristic. This red line tells me about the MOSFET characteristic. Now here you see, it is having some value of on current and some value of off current. And the swing is limited to 60 millivolt per decade, which I discussed in my previous slide also. So now we have to go close to ideal. We have to make my MOSFET towards the ideal characteristic. So what our intention should be? Our intention should be to get on current high, off current low, and it should switch quickly. So now just see this. This is a small swing switch. So it has higher on current as compared to MOSFET. It has lower off current as compared to MOSFET, and it switches abruptly. And this term is nothing but subthreshold swing, which I have discussed in the previous slide. So small swing switch can rescue the problem of subthreshold swing limited to 60 millivolt per decade. And this could be achieved by lowering the body factor or transport factor. Body factor and the transport factor I had discussed just in the previous slide. So there are mainly two mechanisms to reduce the subthreshold swing, which is either alter body factor or transport factor. Now I'll move on to the next slide. So this is an important slide. This tells us about the phase space of MOSFET. So on x-axis I have taken the transport factor, on y-axis I have taken the body factor. So now we'll go one by one. So n is my transport factor, m is my body factor. Here this 1 is there, and here is this 60 is there. Because body factor was what? 1 plus C depletion by C oxide. And transport factor was what? 60 millivolt per decade. Now first we'll go to tunnel FET. The tunnel FET I have kept here deliberately because for tunnel FET m is greater than 1 and n is less than 60. So in tunnel FET we are changing the transport. Like in MOSFET, what is happening? There is a drift diffusion. The electrons are going over the barrier, crossing the barrier, and that is how current is flowing. But what happens in tunnel FET? Tunnel FET, there is a tunneling of electron from valence band to conduction band. So entire transport is changed. Because in MOSFET what was happening? There was drift diffusion. So that's why your subthreshold swing was limited to 60 millivolt per decade. But here the transport is changed. You can see m is greater than 1 means body factor remains same, n is less than 60 means I have changed the transport. The mechanism by which the electron is moving from source to drain is changed. So here I would be able to get tunnel FET. This particular device, there are many devices, I have taken only one. Tunnel FET, IMOS, these are the devices in which the transport is changed and subthreshold swing is below 60 millivolt per decade. Now let's move on to this one, Boltzmann FET. Now Boltzmann FET, I have deliberately kept it here. Now you see, n equals to 60 or it can be greater also because 1 plus C depletion by C oxide. And m is greater than 1. So Boltzmann FET means the conventional MOSFET or SOI or tri-gate, gate all around, all these comes in this Boltzmann FET. So here I would not be able to scale my subthreshold swing below 60 millivolt per decade. Now comes this Landau FET. Now here what is happening? M is less than 1. M is less than 1 means what? M was body factor and N was the transport factor. Now M is less than 1 means I am changing the body factor. So if body factor is less than 1, your subthreshold swing was combination of body factor and the transport factor. The transport is still 60 and this is less than 1. So 60 multiplied by something which is less than 1 is obviously going to be less than 60. Quite obvious. So this is Landau FET. Now let's move to this FET, super FETs. In super FETs what is happening? We are altering both. Both means body factor as well as the transport factor. So devices like NC tunnel FET, NC IMOS comes under this category. And subthreshold swing will be very less because you are modifying both the factors. Body factor as well as transport factor. But the work which I have done The work which I have done is related to land offsets. I have worked here in this region where I am keeping the transport same. Transport same means the transport same as MOSFET. Whatever is transport is happening in MOSFET, same transport is happening in my device. But I have tried to alter M. M is nothing but body factor. I have tried to alter body factor. And how can I do this? I am trying to make M less than 1. Because M is what? M is nothing. M equals to 1 plus C depletion by C oxide. Now I have to make this term less than 1. And it is nothing, 1 plus something is there. So this can be less than 1 only when this becomes negative. So what I have done, there is a material which is known as ferroelectric oxide or ferroelectric material, which is known for providing the property of negative capacitance. So somehow if I am able to make this oxide capacitance negative, this factor goes less than 1.
Yes.
So what I have done, I have used this ferroelectric oxide which is the property of negative capacitance, and that can overcome the Boltzmann tyranny and reduce the subthreshold swing below 60 millivolt per decade.
सर ये शुरुआत ही है.
I think, sir, I have gone 8 slides are over. No problem, these are initials only. Now, let's go a bit into ferroelectric oxide. Although I am not an expert of materials or oxide, I have just taken the parameters of certain oxides and utilized in my device. Let's go through it. So, ferroelectric materials are known for the property of negative capacitance. There are few materials known as lead zirconium titanate, barium titanate, which are well known for, these are perovskite material and they are well known for the property of ferroelectric. Now, but the problem with these material is like lead zirconium titanate. Lead is a poisonous material. All of us know lead is a poisonous material. And use of this material is banned in many countries. Lead zirconium titanate. And there is one more material known as BATiO3, barium titanate. Both of these materials, one problem with this PZT was the toxic nature of lead. And both of the material have a problem of higher ferroelectric thickness requirement. So if you want to design NCFET out of these two materials, the ferroelectric thickness required is in range of hundreds of nanometer. And at present, the feature size currently which we are working on is, the industry research is going on is around 3 nanometers. Suppose a device is of source and drain separation is 3 nanometers and the oxide requirement is hundreds of nanometers. That doesn't suit actually. So after this, some research went on and many doped HFO2 materials came out into picture. And these materials are known for providing the property of negative capacitance. So if you dope, many materials are there, silicon doped HFO2, aluminum doped HFO2, yttrium doped HFO2. So these materials actually provide the property of negative capacitance. Now,
There is some specific name of HFO2.
hafnium dioxide. So if you are doping with these materials, it shows the property of ferroelectric. And these materials which I have noted over here, doped HFO2 material, these require a thickness of 10 nanometer minimum. But this PZT and BATiO3 were in hundreds of nanometers, sometimes 300, 200. So when these materials came into picture, the ferroelectric thickness requirement gradually came down. But still, there is a additional requirement of doping. Like you have to dope your HFO2 with silicon, aluminium. So what happened? One research came into existence, that is undoped HFO2, the normally hafnium dioxide, when it is deposited or deposited with PVD, it gives us the dielectric behavior. But when it is deposited with CVD, chemical vapor deposition, it behaves as a ferroelectric. So instead of going for doped hafnium materials, hafnium dioxide materials, we can go for undoped HFO2 when we are depositing it with a process known as CVD, chemical vapor deposition. And it simplifies the process actually. You don't require any doping, additional doping of hafnium dioxide.
So we are discussing for NCFET.
Yeah, NCFET only, sir. So these are the ferroelectric materials I am discussing. Now, this is the thing which I think some part of it I have already touched in the yesterday's lecture. Now, because here I am discussing about ferroelectric material, I need to discuss how ferroelectric material is different from the dielectric material. Now, we see here, this first curve is charge versus voltage. This AU is arbitrary unit. Arbitrary unit means I have not worried about the what should I say? I have not worried about the scale, but how the it varies, that is more important. Arbitrary unit, AU. So everywhere you can see this is AU. Now let's go to the first characteristic. First characteristic is charge versus voltage. Now, if you see here, the gradient of this line is positive. Now we all know the relation which is Q equals to CV. Q equals to CV. And the characteristic is on y-axis I am having charge and x-axis I am having voltage. So the slope of line is positive. So it confirms the presence of positive capacitance. Capacitance is positive. Now, here I have written Q equals to CV for dielectric. Now similarly, let's now move on to ferroelectric. Now ferroelectric, the relationship between voltage and charge is a bit different. It is a bit different. So that is TFE times 2 alpha QF plus 4 beta QFQ plus 6 gamma QF to the power of 5. Now, these are the anisotropic constants, alpha, beta and gamma. So these can be calculated by using the corrosive field and the remnant polarization of the material. So if you put these anisotropic constants and you try to plot, you will get charge versus voltage like this. Now if you see here, in this range to this range, when you are increasing the voltage, there is a decrease in charge. So gradient will be what? Gradient will be negative. So that is nothing but, so in this particular range, my oxide is what? My oxide is providing me the negative capacitors. So this was the dielectric capacitance and this was the ferroelectric capacitance. Now, so this tells me that negative capacitance exists in the ferroelectric material. I have plotted. Now, let's confirm the same thing. Let's confirm the same thing using energy curve. So this curve is energy landscape curve of a normal dielectric. And the relationship is U equals to Q square by 2C. So if I try to plot, this is energy U and this is charge. So obviously this is an upward parabola. So this tells me that this is a positive capacitance. Now, the relationship of energy and charge in ferroelectric is given by U equals to alpha QF square plus beta QF to the power 4 plus gamma QF to the power of 6. Now, if you get the values of alpha, beta and gamma, which are the anisotropic constants, you will get the characteristic like this. Now, in between this region, this charge to this charge, there is an inverted parabola. Inverted parabola means radius of curvature is negative. So this, in this particular region, your ferroelectrics behaves as a negative capacitance. So you can say by these graphs, you can say that negative capacitance exists in ferroelectric oxides, and this has been given in this article also. These equations which I am referring to are actually given by these two scientists, L. D. Landau and I. M. Khalatnikov, and that this equation is basically known as LK equation, which is Landau-Khalatnikov equation. Now, just now we have seen that negative capacitance exists in a ferroelectric oxide. So this is one of the setup which I have taken from one of the article, one of the thesis in Berkeley University, I think. UC Berkeley. Now what they have done? They have taken a parallel plate capacitor in which the material is a ferroelectric material. They have taken a parallel plate capacitor with a ferroelectric material. Now, as we discussed in our previous slide, what has happened? It should show the signs of negative capacitance. But when this is put across impedance analyzer, this is an impedance analyzer, you can see it is showing a positive value of capacitance. You can see Cp equals to 46.9230 nanofarads. When the capacitance is fabricated, it should show by our logic what we discussed in our previous slide, but it is showing a positive capacitance. Now how this is happening, that we need to understand. So this is what I have written over here. Ferroelectric capacitor when connected to impedance analyzer shows positive capacitance. Why this is happening is the negative capacitance state in ferroelectric is very unstable in nature. Negative capacitance state in ferroelectric is very unstable in nature. That's why when you are connecting it across impedance analyzer, you are seeing a positive capacitance only. Negative capacitance is not visible. Now the question arises is, just in my previous slide I told it is showing the signatures of negative capacitance, and in the next slide I am saying that one experiment was done, and in that experiment UC Berkeley one scientist did this, and the impedance shown was positive. Now one question which arises is, how can we confirm the presence of negative capacitance? Because it's showing positive. So for this, what I need to do, it's not showing because the state is, the negative capacitance state in ferroelectric is volatile. Now, how can we confirm that there is a negative capacitance? For that,
We have discussed all these things yesterday.
yeah.
Further, you will say that we can show it by adding a one capacitor.
Yes.
Series with it.
Yes.
So I think better to discuss the application part.
Yeah. I'm coming on to that. Slowly, gradually, but because sometimes the audience changes, so I have to go through the basic only. So this is the thing. So we need to add a dielectric capacitance in series to ferroelectric capacitance. Then we can confirm the presence of negative capacitance signature features. Now we see here, this is for dielectric, and this is for Fe plus D heterostructure. Now here you can see that slope of this line is obviously higher than this. So we can say the capacitance here is
Positive.
higher, and higher capacitance is only possible when two capacitance are in series, only if one of them is negative in nature. Similarly, UQ, this is the characteristic for dielectric, and this is the characteristic for Fe plus D heterostructure. Now this curve is more flat as compared to dielectric curve. So this is flat, means the total capacitance of heterostructure is more as compared to this case, DE case, dielectric case. So again the total capacitance is higher. Total capacitance is higher means it's not possible in normal to positive capacitance, because C equivalent equals to C1 into C2 upon C1 plus C2. So equivalent capacitance has to be less. But here I am getting more capacitance, which is actually the violation of Kirchhoff's voltage law. But that violation only tells the presence of negative capacitance. Similarly, I think these graphs I showed in the top one also. So this is VD versus VS. VD is voltage drop across dielectric and VS is the supply voltage. So here you can see the voltage drop across the dielectric is more than the supply voltage. And this is not possible in normal two capacitors which are positive. That is only possible when there is a negative capacitance. So look at the beauty. The voltage drop is higher than the supply. So this is one table. I think this table I showed yesterday also. So this is C1, this is C2. C1 is the fixed capacitance or fixed and positive. C2 is a variable capacitance which I am varying from 4 to -7. So this in entire table C1 is fixed, C2 I am varying from 4 to -7. So till 0, what is happening? The parallel combination is C equivalent is smaller than C1. This is what I was telling. When two positive capacitance are in series, what is going to happen? The equivalent capacitance will be less than.
Yes, yes.
So C equivalent is smaller than C1. Now, once it goes to negative, just this part, this is interesting. C2 becomes negative, -1, -2, -3. This case, the C equivalent itself is negative in this case.
Yes, sir. Fourth one is the negative.
And this is C equivalent is undefined. The interesting case arises over here from -5 to -7. What is happening? The equivalent capacitance is 20, 12 and 9.3. So it has actually become more than each of them. This was 4, this was -5. Equivalent is 20 more. So C equivalent here is larger than C1. Now here an important thing to note is when you are trying to get amplification in FED heterostructure, what should be the condition? Mod of C2 should be greater than C1. Then only you will get the faithful amplification or proper amplification. If your C2 is in this range, then it's no use. It has to be mod of C2 has to be more than C1. Then only capacitance enhancement and voltage amplification is possible. Now, the application of this part, negative capacitance field effect transistor. So you can look this device as, if you see this is a substrate, source, drain, oxide and metal. If you only see this part, if you neglect this top metal and bottom ferroelectric, this is nothing but a MOSFET. It is nothing but a MOSFET. So what I have done, I have just added a ferroelectric on top of it. So here you can see this has become a heterostructure, which I have discussed. Now, your NCFET is nothing. NCFET is just a MOSFET with an external amplifier. So their ferroelectric is acting as a amplifier.
Oxide metal then ferroelectric.
Yes, yes.
ये then metal है.
Yes. So it's like you have a MOSFET, correct? Metal is there, okay, and I have fabricated a ferroelectric capacitor. So there will be metal at top, metal at bottom. There is one metal here also. So this metal is getting connected to this.
So oxide wave like a dielectric.
Which oxide, sir?
Yellow.
Yellow is that is the dielectric, normal dielectric, which is present in the conventional MOSFET also.
Yes. ठीक है, yes.
Now this is the capacitance model for NCFET. So there is a depletion capacitance, source capacitance, drain capacitance, oxide capacitance. If I neglect this ferroelectric capacitance, it is nothing but a MOSFET only. And in order to realize this ferroelectric capacitance, I have written CF. CF stands for ferroelectric capacitance. And this is the gate voltage, source voltage, drain voltage and body voltage. So this is what I have written. NCFET can be considered as a conventional MOSFET only with a external amplifier, because purpose of ferroelectric is to amplify, and with equivalent capacitor divider circuit of this is what I have written, an external amplifier which amplifies the gate voltage. Now what we have done, we have taken the value of what we have taken actually for undoped HFO2, which I discussed in my earlier slides, has corrosive voltage 100,000 kilovolt per centimeter and remnant polarization is 100 microampere per centimeter square. Now this is what one thing. So this the model for this NCFET we have taken from NanoHub, and we have done some calibration, some modifications in order to incorporate undoped HFO2.
अनडोप्ड HFO2 का मॉडल था वो?
No, a normal model was there, so we modified it for undoped HFO. So because we have done some modifications, so there is one test known as Gummel symmetry test, which tells the symmetry of device. Like many times we say that MOSFET is a symmetric device. The source and drain can be interchanged. So there is one test known as Gummel symmetry test. This we have done, and we found that drain current Ix is an odd function of Vx. So that tells that the device is symmetric in nature. And higher order derivatives are continuous. No singularity exists at Vx equals to 0. Hence this passes the GST test. GST here is not that GST. Gummel symmetry test.
Where x is the distance.
No, x is this Vx.
अच्छा okay, V1 V2.
Vx and minus Vx. So this is known as GST, Gummel symmetry test. This we have done to validate whatever we have modified. We have something. So that model only says that Ix should be odd function of Vx, and there should not be it should be continuous, or no discontinuity should be there at Vx equals to 0.
That's why one part is positive, another.
Yes. Now the next slide.
Sir, वो graphical behavior for
Nothing much.
Same ही है.
Just it is odd function. What GST says is Ix should be odd function of Vx.
What about at 0 point?
Which point, sir?
0 the center point is.
It's odd now. And higher order derivatives should be continuous. So this passes our Gummel symmetry test. Now here comes a few results. Now I think in my talk number 1 I was telling a few things about hysteresis, but I did not explain what is happening, what hysteresis is actually. And if I go to my previous slide, I showed that when mod of C2 is greater than C1, then only amplification is there. Now, we'll try to analyze this, what is happening. So there is one characteristic in, these are now the results of NCFET, not heterostructure. So previously the results in talk number 1 was with respect to heterostructure. Now this is the results of NCFET. Now there is charge versus gate capacitance. This characteristic is there. Now, this TFE is varied from 0 to 15 here.
Which thing, sir?
TFE, ferroelectric thickness. This thickness.
Okay.
This thickness is varied from 0 to 50. Now, if this TFE equals to 0, what is going to happen?
It is behave like a simply dielectric.
No. TFE is there. Means no ferroelectric is there.
No
Then
ferro-
two metals are there. Metal, it's a MOSFET only.
MOSFET only.
So whenever TF equals to 0 case comes, that means we are discussing about
Simple MOSFET.
simple MOSFET. I hope you guys understood what I'm trying to explain. When TF equals to 0, nothing is there. It's a MOSFET only. So whenever there is a case of TF equals to 0 in our analysis, we should come to a conclusion that we are discussing about MOSFET. Whenever some ferroelectric thickness is there, we can call it as NCFET. Now,
So full form of NCFET?
negative capacitance field effect transistor. Now, just few slides back, I told you about LK equation, Lanov-Khalatnikov equation. So there we got one relationship between charge and voltage.
Yes.
There was one relationship between charge and voltage. Now capacitance is what? Q equals to CV, so C equals to dQ by dV. So if I differentiate that particular equation, I should be getting the equation of capacitance.
See,
So from there, I have got
this.
CFE. What is CFE actually? CFE equals to 1 upon TFE into 2 alpha. It's quite obvious. Now, what is the interesting thing over here? Can I get one glass of water? Just please hold on for a second. So, should I continue? So, interesting thing to note over here is,
Reverse phenomena.
no, not reverse. This is inversely proportional to TFE. CFE is inversely proportional to TFE. That happens in dielectric also. Dielectric, what is the capacitance? C equals to epsilon A by D. D is what? Separation between the
Distance.
two plates.
Yes.
So here it's an inverse function of TFE. So more the thickness, less the capacitance, less the thickness, more the capacitance. So it's inversely proportional. CFE is like this. Now, what should happen? Like if I increase TFE, CFE should go down. Correct? Now let's try to analyze this particular graph. Now, this graph corresponds to TFE equals to 0. TFE equals to 0 means TFE 0 is MOSFET. So this graph is for MOSFET. Now, this blue, not blue, green. Green corresponds to 5 nanometer. Blue corresponds to 10 nanometer. And brown corresponds to 15 nanometer. Now, as you are increasing the thickness, the capacitance is decreasing. It is going from higher to lower. Just see. It is going like this, in this direction. But there is one interesting thing happening over here. The interesting thing is, when TFE equals to 5 nanometer, this is lower and this is higher. Correct? Similarly, when TFE equals to 10 nanometer, these two are very close to each other. Just see this red and blue characteristic. And when TFE equals to 15,
They are equal.
not equal actually. Just see this brown characteristic. It has gone ahead of it, so it becomes lower. CFE becomes lower than CMOS. Now, whenever this condition happens, that CFE becomes more than CMOS, there will be hysteresis in the device.
Sir,
Like what I told here, just a second, sir. Let me complete. Like this comes from here. So mod of C2 should be greater than
C1.
C1. Similarly, like this.
सर इधर तो इनिशियली कमी है ना वैल्यू इसकी अलग अलग जैसे
नहीं ये यहाँ पे बात कर रहा हूँ मैं, दिस रीजन.
नहीं जैसे ग्रीन से चले
हाँ
तो कम है उस रेफरेंस से जीरो
हाँ इससे रेड से कम. वी हैव टू कंपेयर विथ रेड बिकॉज रेड करेस्पॉन्ड्स टू मॉसफेट.
रेड करस्पॉन्ड
टू मॉसफेट.
हाँ इसी से कर रहे हैं.
हाँ.
जो नेक्स्ट है वो रेड
हाँ.
नहीं है ना, ये क्या ब्राउन है ना.
हाँ ये ब्राउन है.
कितने मीटर है?
15 नैनोमीटर.
15 नैनोमीटर. तो इस पे वैल्यू डाउन हो रही है.
हाँ
बाकी पे तो वो
हाँ.
डाइलेक्ट्रिक
हाँ.
का जा रहा है.
So that is what I am telling. At TFE equals to 15 nanometers, there will be hysteresis. Both other two cases are fine. No problem with other two cases. The problem arises only at
15 nanometer.
15 nanometer. And actually we should not say as a problem, because sometimes problem also may be taken as some application, because hysteresis is, because I am saying it as disadvantage. Why? Because I am trying to go for digital application. If you go for memory kind of application, hysteresis is very good.
Yes.
So because I am trying to use this device in digital application, that's why I am saying it as a, so for me it is a disadvantage, because I am trying to design it for digital application. So hysteresis comes. Now what is hysteresis actually? I'm coming to it, sir. Now let's go to this AG versus VG. So before that, just a second.
In your table, at what value there is a certain limit up to 15 or in this table -7?
No, that table I have just
So,
take
there is-
roughly,
Okay.
means that has nothing to do with
Okay.
these are some random numbers which I have taken just to make the audience understand in quick fashion or quickly. Now, before I go, no, not this. Yeah, not this. Okay. So, there is one term known as VMOS. VMOS. If you are able to see here, this is VMOS. This one.
Yes.
Now, if you solve this particular, there is a lengthy derivation for this. If you solve what is the potential at VMOS, it comes out to be AGVG plus ADVD. Here it is quite obvious. This is gate bias. Then you can come this side. And this is nothing but and AG is amplification factor. Amplification factor AG, which can be written as mod of CF upon mod of CF minus CF. And similarly, this is AD is drain coupling factor. Drain coupling factor. This is nothing but CD upon mod of CF minus of CMOS. So there is a lengthy derivation. I am not going for the derivation, but VMOS is AGVG plus ADVD. And here I have plot AG versus VG. So AG is nothing but amplification factor, gain. Now you just see this red curve. Red curve corresponds to MOSFET, TFE equals to 0. So there is no amplification. Obviously there won't be amplification because when this CFE is not there, when CF is not there, VG equals to VMOS. So there is no amplification. So this is a straight. Now, as I increase TFE equals to 5, as I increase the thickness, ferroelectric thickness, TFE equals to 5, you can see there is an amplification. Similarly, when TFE equals to 10 nanometer, there is more amplification. There is more amplification. Although after this point, the amplification is not there. This is why it is not there, because of non-linear behavior of your ferroelectric capacitance. Ferroelectric capacitance is non-linear, not like dielectric where the linear relation exists. Now, the interesting case happens here. TFE equals to 15. Now, are you able to see this characteristic, brown characteristic? So when I'm sweeping it from 0 to 0.9, it is going like this. When I'm sweeping back from 0.9 to 0, it is going like this. So kind of hysteresis.
Yes.
When you are sweeping in forward direction, the curve is going in different. And when 0.9 to 0, it is coming back at some different place. So this is hysteresis, and this is what I am trying to avoid in my digital application. I don't want this. Obviously, this is a disadvantage in digital application. So what should I say for my digital application, because I am targeting the digital application? My critical thickness is 10 nanometer. I should not exceed the thickness beyond 10 nanometer. If I increase it beyond 10 nanometers, the hysteresis comes into the device. And there is an expression for TC. This is 2 by 3 root 3 Q naught upon EC into CMOS. Now, the amplification is maximum when? The amplification is maximum when, just see, these two curves come close to each other. So this was the CFE, correct? And this was for MOS. When CMOS and CFE comes close to each other, there is maximum amplification. The same thing can be confirmed from here also. Like here it is 4 and minus 5, correct? 4 and minus 5. So what is the capacitance? 20. If you make it 4 and 4.01, 4 and minus 4.01, you will get maximum amplification. This is what is happening here. When these two are close to each other, you are getting maximum, and you cannot increase the thickness randomly. Like if I have to improve the performance, you cannot say I'll put 100 nanometer. There is some limitation, because if you go beyond that, hysteresis appears in your device. Although if you are going for memory application, you can obviously have to exceed the thickness beyond critical thickness. For memory application, for digital application, it should be well within TC.
We have to select a single value or range from 5 nanometer to 10 meter.
You can take any value,
But there is
but at 10 nanometer it will give the best performance. Best performance. So because here I started with a interval of 5 nanometer, so I have kept the interval as 5 nanometer only. If you increase it just above also 10 nanometer, it will be, hysteresis will come.
Yes.
Because previously I have taken the interval as 5, so I have continued with the interval of 5. So I hope this
optimum value is for 10 only.
10 only. But it all depends actually, because here I am having 32 nanometer MOSFET. Suppose you go for a design of like 45 nanometer MOSFET. So not necessary critical thickness will be 10, because everything is dependent upon matching of two capacitance.
Okay.
Like here for this I showed now. This is C1 is fixed, 4. Now this C2 is variable. Now where two capacitance are matching close to each other. If you go for 45 nanometer, maybe this C1 is changed, CMOS is changed. Then that thickness will change.
That is depend upon C1.
Yes. It depends upon both actually, matching of both.
Matching of both, that's why ultimately.
So when they matches closely, then best performance is obtained. Yeah. So this is what I am saying. TFE equals to 15. CFE is less than CMOS. So this is CFE, brown curve, and CMOS is this red curve. Hysteresis hence
start appearing
in, I think something I have missed. Hysteresis starts appearing. There is some one word is hysteresis starts appearing in the NCFET characteristic. Sorry for that. Now, next is now this becomes very simple once this basics.
I have lecture.
No problem. Thank you. So now we have one more characteristic, that is charge versus voltage. Now everything is simple. Now as I told, I'm going for digital application, and I know at TFE equals to 15 nanometer, hysteresis will come. So from here onwards, I have not discussed the case for TFE equals to 15. I have restricted myself to TFE equals to 10. Even if you go to my title is Insight into Non-Hysteretic Negative Capacitance Field Effect Transistor. So NCFET which does not have hysteresis.
Yes. Okay.
So let's go to this case, charge versus voltage. So this is quite simple, that TFE equals to 0 means corresponding to MOSFET, this is the one. And for TFE equals to 5 it increases, and TFE equals to 10 it increases. Now the capacitance. What happens to total capacitance? Or gate, not total, total, but gate capacitance. Now what will be gate capacitance? It is series combination of
C1 and C2.
C1 and C2. And particularly C1 is means one is MOS and one is ferroelectric, because below ferroelectric there is a MOSFET. So CF, CMOS, CF, CMOS, the series combination. Now just now I have told CF upon CF minus CMOS equals to AG. Here, this is AG.
Okay.
can I write CF equals to CMOS times AG? Yes, I can write this is CF upon CF minus CMOS. So AG times CMOS. So what happens? CG is series combination. That is clear. Now this term, if you see this term, CF upon CF minus CMOS, that is equals to nothing but this AG.
Okay.
So what I have written instead of
Okay.
CF upon CF minus CMOS, I have written AG. So AG times CMOS.
Yes.
So total capacitance is increased. The gate capacitance is increased. If you see, for TFE equals to 0, this is the capacitance. For TFE equals to 5, this is the capacitance. And for TFE equals to 10, there is an increase in capacitance. This is the same thing which we have already discussed in heterostructure also.
We have discussed the graph for AG na previously.
Yes, AG.
So AG increasing, that's why CG is.
Yes. Because AG is what? Amplification, and we know that in NCFET the basic principle is amplification.
Okay.
Now, we are moving close to the device part. Now this is VMOS versus VG. VMOS was what? If I go back, VMOS is this potential, and VG is this potential.
Okay.
And here only I am supposed to get amplification, VMOS.
Yes.
Now let's see this characteristic. Now, so this is for TFE equals to 0, means conventional MOSFET. That will be linear characteristic only. But this is TFE equals to 5. Now if I see here, when VG equals to 0.9, it is close to 1.2 something. So amplification has occurred. This is VG. VG is 0.9, and I am able to achieve here 1 point something. So there is an amplification.
Yes.
And like for the case of TFE equals to 10 nanometer, VG is 0.9, and this goes around, this is the curve, I think. Yes, this is the curve. So it's between 1.5 to 2.
And in blue graph, it is for 0.9. It is
VMOS equals to
1 point something.
1 point something. So obviously amplification is there. Now, there is an interesting case over here that comes at VG equals to 0.
Yes.
What is happening at VG equals to 0?
Both are 0.
At TFE equals to 0, it is 0. If you zoom in and see, at TFE equals to 0, it is perfectly 0.
It is
What?
slightly higher.
Slightly lower, sir.
Lower actually.
It goes to minus.
Okay.
So this TFE equals to 5, the value is negative. And for TFE equals to 10, it is more negative. Now why it is happening?
Okay.
Why it is happening? So here I told VMOS equals to AGVG plus ADVD. Correct? Now this is, if I put this value here and I put this value here. Correct? Now at this point, VG equals to 0. So should I put VG equals to 0?
Okay.
So VMOS is what?
Yeah.
ADVD.
Yes.
Correct?
Okay.
Now what is? VD is positive. Positive bias is applied. 0.9. You can see VD equals to 0.9.
कहाँ? अच्छा 0.9. Okay.
This one. This one.
ऊपर है.
हाँ.
Okay.
Now AD. What is AD actually? Minus CD upon CF minus CMOS. So there is a minus sign. So that is why at VG equals to 0, my VMOS is negative. Now whether this is advantageous or disadvantageous, we will discuss in the next graph.
I think initially it is disadvantageous at the when the current starts flowing.
No, actually, sir, it is advantageous. Why? Because in any switch, what do we want? We want on current to be high,
Yes.
off current to be low. Low, obviously low. Off.
It is the case of starting on current low.
What, sir? Once again.
It is the case for starting starting current.
No,
which
this is at present. This is potential, sir. This is potential.
Okay.
Potential at this node. VMOS. This node.
Okay.
Now I'll come to it how it is advantageous or disadvantageous. Now what I want, ID versus VG characteristic. The ultimate aim for like
ID
device engineer, ID versus VG. Through ID versus VG only we discuss everything. Now if you are able to understand this, everything we have understood. Now let's go to this red curve. Red curve corresponds for TF equals to 0 nanometer.
Yes.
0 nanometer means
Dilate.
MOSFET.
MOSFET.
So this is the characteristic. This is the on current and this is the off current.
Okay. ठीक है.
Okay. Now TF equals to 5 nanometer. Now what happens? TF equals to 5 nanometer. I was applying 0.9 over here, and what I am getting? More than 0.9.
Yes.
Obviously, this current will increase. If you go here, this I am applying here 0.9. I am getting more than 0.9.
Yes.
So it's like NCFET. I already told NCFET is like MOSFET with amplifier.
Yes.
So you applied less, you are getting more. So obviously current is going to increase. So this is why it is happening here. You see, this current is increased. Now the next part. If you see the off current means at 0, VG equals to 0. The off current is lower as compared to the case of MOSFET.
Yes.
Now why it is happening is just now explained.
Yes.
This VMOS is going negative. So when VMOS is negative, so at VG equals to 0, VMOS is what? Negative. So negative means obviously off current has to come
Yes.
down. So what I have done, I have increased my on current and decreased the off current. So this is of great advantage to me.
नहीं आया समझ.
In a switch, on current should be high, off current should be low. Now you consider the case of MOSFET, red line. There is some on current, there is some off current. Now with the help of ferroelectric material, what I have done, I have increased the value of on current and I have decreased the value of off current.
Okay.
And that is what our intention, what initially in initial side I was discussing about the switches. Switches should have two states, one is on state, off state. In on current, should be, on state current should be as high as possible. In off state, the current should be as low as possible.
Okay.
And the switch should turn on abruptly, means at small value of gate
Yes,
voltage,
yes,
it should
yes,
switch.
Yes.
So now two advantages we got. One is
Less off current
and
more
more on current. Now one thing that I was discussing just now, it should switch quickly.
Yes.
In within less voltage, it should turn on and turn off.
Yes.
So that comes with subthreshold swing. And I told that in MOSFET this was the biggest limitation, that subthreshold swing is below 60 millivolt per decade. Now let's see. This is the characteristic for subthreshold swing. Now here I have taken subthreshold swing is nothing but log derivative of variation in gate voltage with respect to variation in log IDS.
Log.
Log IDS current. Here I have shown.
Ideas. Okay.
Just a second. I think
ठीक
you.
है. It is nothing but ultimately the
हाँ,
change in
yeah.
gain current with respect to
हाँ.
gate current.
No, inverse of that. That is subthreshold slope. I am talking about subthreshold swing.
Okay.
This del VG upon del log IDS.
अब इसके बारे में ज़्यादा बताएं क्योंकि ये टर्म कई बार आती है.
हाँ.
Subthreshold
So,
voltage.
should I explain once more this thing? Or at last, if you say.
Yes. अभी बता
अब
दीजिए.
बताइए, subthreshold swing. Okay. Subthreshold swing, SS, is actually the slope of, inverse of slope of subthreshold slope. There are two terms and confusing terms, subthreshold slope and subthreshold swing. Slope is nothing but y by x. Slope is nothing but
नहीं,
y by, no, I just want to, slope is m equals to y by x. Now I am having log ID over here
Okay.
and VG over here.
Okay.
And my characteristic is something like this.
Like this.
In subthreshold, if you separate the name sub,
Threshold.
threshold. So sub threshold means I am talking below threshold, sub.
Yes.
So you have to judge the slope before threshold. You
Okay.
don't have to judge the slope here. Before threshold.
In this part,
Here.
linear region almost.
So here you have to judge the threshold. Now slope will be what?
d by dx.
Yeah, just a second. I hope I am on time because other speaker has to come.
It will come at around 4:30.
Okay, so fine, I'll continue. Now, sub-threshold slope. Sub-threshold slope. Slope is y by x. Sub-threshold means I am going below threshold. So it is nothing but del of log ID by del of
Log Vg.
Vg. And swing is what? Now sub-threshold
Which t here, suppose.
swing. Swing is SS inverse. Means sub-threshold slope inverse. So this will be what?
I think it is a
Del-
rate of change of threshold.
Del of Vg upon del of
ठीक है.
this is your sub-threshold slope. This is slope, this is swing. So in case of MOSFET, this is a small derivation for it. So if you solve it, it comes out to be 2.3 kT by cube, 1 plus C depletion by C oxide.
Okay.
And I think I told in the yesterday's lecture also, 2.3 kT is Boltzmann constant, T is the temperature, Q is the electronic charge. When you put these values, it comes out to be around 60.
Millivolt per.
60 millivolt. And plus 1 into, multiplied by 1 into something. So obviously 1 plus something is more than 1. And if you multiply 60 with 1 point something, it has to be greater than 60.
Yes.
So in MOSFET it cannot be scaled below 60. So that is why we have gone for this NCFET here. So just a second. So here important thing to notice, this is log, not ID actually, log ID. Now I have log ID versus Vg with me. For sub-threshold swing, what I have to calculate? Del of Vg by
Log of ID.
log of ID. So here what I have done, this is SS. SS means del of Vg by log ID versus Vg. Why I have taken only up to 0.3? Because this is sub-threshold. Sub-threshold means I have to discuss the things below threshold. Just a second.
Thank you. ठीक है, मैं चल लूँ.
Okay. So I was saying I have taken only up to 0.3 because we have to discuss for sub-threshold. Now this is the characteristic. Now just see at TF equals to 0. TF equals to 0 corresponds to MOSFET. MOSFET you can see nowhere it is going below to 60. This is the 60 line. It is above 60. Now this is for TF equals to 5 nanometer. It has come down but not below 60. Now just see here at TF equals to 10. It has gone below 60 and it is approximately equals to 45 millivolt per decade. So sub-threshold slope has been reduced to
मैं 45.
45 millivolt per decade. And if you solve it by expression also, the sub-threshold slope of MOSFET is 60 millivolt per decade into 1 plus SIP depletion by its C oxide. And for NCFET, it is actually divided by 1 by Ag. Ag is the amplification factor.
ठीक है.
Now we are discussing the transconductance. Transconductance is what? Del of ID versus del of VG. That is quite obvious. So the transconductance of NCFET is Ag times the transconductance of MOSFET. Now we see here, this is the transconductance for MOSFET. This is the transconductance for NCFET at 5 nanometer, and this is the transconductance of NCFET at 10 nanometer. It has increased. Now threshold voltage.
But it is on the cost of the value of SS less than 60.
But we want our value to be less than 60.
Okay.
It is advantageous. Now threshold voltage. Now there are many ways to calculate the threshold. Although in device physics we say threshold voltage is that voltage at which, or the voltage at which the electron, the hole concentration in the bulb is equals to electron concentration in the channel. As per the standard definition in the device physics, the threshold voltage is a voltage at which the hole concentration in the body or bulb is equals to electron concentration in the channel. That voltage will be called as threshold voltage. But there are many methods, means as from characteristic we can get the value of threshold voltage. One is intercept method, second order transconductance method, many methods are there. Here I have gone for second order transconductance method for calculation of threshold voltage. Now, so this method says, what actually this method says, you have to take the derivative of current in second order. Means transconductance is what? Del ID by del VG. Second order transconductance means second differentiation of current with respect to voltage. Means I'm saying like this. GM is what? GM is del ID by del VG. And GM2 means second order transconductance, means that is equals to D2 ID by VH. Second transconductance. So what I have done, I have taken the second transconductance, and this method says the value, the gate voltage at which the peak of this characteristic comes is your threshold voltage. So let me just reiterate it once again. Second order transconductance method is a method to calculate the threshold voltage. This method says you have to take the second differentiation of current with respect to voltage and the gate voltage, and the gate voltage at which the peak is coming is known as your threshold voltage. Now we'll just see the peak for this is coming, TF equals to 0 is coming at 0.27. For TF equals to 5 nanometer it is coming as 0.26, and 10 nanometer it is coming as 0.25. So threshold voltage is decreased for NCFET as compared to MOSFET. And there is a mathematical expression also through which I have expressed VTH 0 naught dash, means this is the threshold voltage of NCFET, this is the threshold voltage of MOSFET, and by this term your threshold voltage is getting reduced.
So ये जो वैल्यू आपने ली है TFE की 10 नैनोमीटर, तो जो उसकी MOSFEट की जो थिकनेस है वो किसी पर्टिकुलर वैल्यू के लिए ली होगी?
MOSFET की thickness means what sir?
मटेरियल जो डाइलेक्ट्रिक मटेरियल जो आपने
हाँ
वो किस वैल्यू के से कंपेयर कर रहे हैं आप ये?
No, actually understood sir. You are asking me what is the value of dielectric thickness you have taken.
Yes.
So actually that is not in my hand. Actually I have used 32 nanometer.
Okay.
In 32 nanometer there are set of standard specifications. So for 32 nanometer BC model there will be a fixed value of dielectric capacitance. Dielectric thickness will be fixed, material will also be fixed. So what is in my hand? I have only ferroelectric in mind. So everything is fixed for 32 nanometer. As it is as per the BSIM.
How much
BSIM
is
model.
the actual value?
Actual value, I'm not sure sir, but I think it's 1 or 2 nanometer dielectric thickness. I'm not sure. I will have to see.
We cannot change it.
We cannot change it.
It is a standard.
Yeah, because NCFET is nothing but MOSFET with an amplifier.
Yes, it is fixed for MOSFET.
Yeah. because whenever the things go in Fab Lab, standard values are there, and you have to stick to those values. You cannot bypass those rules. So that dielectric thickness is fixed, and its permittivity is also fixed. If you are taking it as SiO2, it's 3.9. If you are taking hafnium, it's more than 3.9.
Okay.
It's around 20. It's in the range of 20 to 25.
So
this-
it is better, मतलब, in all rates,
Yeah.
TFE equal to 10 nanometer gives better rate.
Better.
Lower
Yes,
threshold voltage.
yes.
And,
More transconductance, lower lower subthreshold swing, higher on current,
yes.
lower off current. Everything is good.
Is there any drawback or not?
Drawback is there, sir. Drawback is there in terms of speed.
Okay.
So NCFET is basically a low power device. So what we are saying here, like suppose I have MOSFET, it has some power dissipation and some speed. Through NCFET, what I want to achieve is, I want to reduce the power dissipation. I'm okay with the speed. Speed, whatever I'm getting with MOSFET is okay for me. Matlab, it all depends upon the application. So where low power application is there, this suits the most.
Speed
But high speed, I'm saying that speed is close to MOSFET.
Okay, अच्छा, okay. Speed तो naturally we are, since the capacitance is increasing.
Yes, so
it
speed has
restricts
to,
the speed.
it restricts the speed. So there is one more term that I have not included here, that is known as rho in this. Rho, because why that thing is not coming here, because I am dealing with static response at present.
Okay.
So if you go for that
Dynamic
elegant equation,
response.
yeah. So what I told you, alpha QF plus beta QF to the power of 3 plus
gamma.
gamma QF to the power of
Six.
5
अभी आप
plus
6 लिख रहे हो.
नहीं सर वो u से
वो U से.
u में 6 है rho dq by dt. So जब मैं static, when I am discussing about static, this has no role. So this I can neglect. But when you are discussing the dynamic response, this comes into picture. And this rho value decides the speed. And rho is a material dependent parameter. So if rho value is less, speed will be high. If rho value is very high, then speed will be very low. Since I am discussing about static response only, so I have gone for this can be neglected.
Mathematically expression से अगर देखें
हाँ.
तो वो मल्टीप्लाई हो रहा है df by dt में, तो ओवरऑल df by dt की वैल्यू तो इंक्रीज हो रही है.
dq by dt है सर. हाँ.
dq by सॉरी हाँ वो dq by dt की वैल्यू
हाँ.
इंक्रीज बढ़ रही है. रो मल्टीप्लाई है ना.
हाँ.
तो अगर रो की वैल्यू ज़्यादा होगी तो
हाँ.
dq by dt की वैल्यू भी ज़्यादा होगी.
हाँ.
होगी तो स्पीड तो फास्ट होना चाहिए.
नहीं कम.
ऐसा क्यों होगा?
Bf equals to alpha. Okay, so you are saying it like this. If as per your opinion, because rho is increasing,
Yes.
this term will increase, no sir. How can it tell about speed? There is no
VF
relation
value
with
of
the
VF
speed.
is increasing. VF
Vf is voltage drop across ferroelectric.
across ferroelectric.
So there is no relation. If this is increasing, speed has to increase, because this is not related to
Not
speed actually.
related with.
If rho goes down, then only speed goes up.
So it means there is some another mathematical relation with respect to speed.
Huh. So because I have not included those results in the slide, otherwise I would have showed you. Means this is my initial work where I have gone for.
I think rho has some relation with overall capacitance.
Yes, obviously it will be there, no, sir. Because if you differentiate this, Q is what? dq by df is what? That is capacitance. Correct enough?
Okay. Just for the sake of simplicity, if we ignore it, then dq by dt equal to vfy
No.
rho. Yes. So less value of rho will increase the value of dq by dt. यही हुआ ना?
So as rho is increased, the speed goes up.
That is the मतलब इसको अगर इग्नोर
Yes,
करें
yes.
ये आएगा इधर.
यदि इग्नोर नहीं करें,
नहीं नहीं
हाँ.
इसको अभी कांस्टेंट मान.
Yes, yes,
सब
yes.
इस टर्म को नीचे ले आए.
Hmm.
ठीक है, vf by q,
Hmm.
df by dt.
Hmm.
This term it is equal to c.
See, yes.
ठीक है.
हाँ.
तो अगर इस टर्म में रो की वैल्यू कम होगी
Hmm.
तो नेचुरली है कि सी की वैल्यू
हाँ, हाँ. In that aspect also we can understand. Yes.
सी की वैल्यू बढ़ेगी.
Yes, yes.
मगर सी की वैल्यू बढ़ेगी तो फिर
C की वैल्यू बढ़ेगी तो डिले बढ़ेगा.
डिले बढ़ेगा. तो
Speed
speed
कम होगी.
होनी चाहिए.
Speed कम होगी.
तो रो की वैल्यू
No, I think, sir, there is here, yeah, this capacitance I have taken. It will be
ओके ठीक है.
plus rho into dq by dt
हाँ,
here,
ठीक है सर.
because you have to differentiate it,
Yes, yes.
and when you differentiate, it will be CFE equals to 1 upon this plus in denominator it will come, I think.
Mhm.
So in denominator, yes. So should I proceed?
Yes, yes.
So I
That
think
is
I
a
have
matter of further discussion. Let it
Ah.
be.
So this is threshold. So there is a mathematical expression also. So this is the mathematical expression. Now we'll go for Dibble, drain induced barrier lowering. So
37 slides are there.
yeah. So yesterday's lecture was a bit crisp and today's lecture is a bit lengthy.
Okay.
Okay. So I'll go through it quickly. So now Dibble is what? Dibble formula is something like this. So it's minus of threshold at high drain bias minus threshold at low drain bias upon VD high minus VD low. Now here we have already extracted the threshold at 0.9. 0.9 means high value of VD. Now the same thing we are doing at VD equals to 0.09 volt. Now using this again the second order transconductance method, we have calculated the value of threshold. So here if you see, this is for high. So this 0.7 to 0.26, sorry, 0.27, 0.26 and 0.25, these values are same because this is for VD equals to 0.9 and these are the values for 0.09. So here value was 0.27, 0.26 and 0.25. Here I got the value as 0.35, 0.25 and 0.17. Now let's calculate the Dibble parameter. So it comes out to be 0.0987 in case of conventional MOSFET. It is positive. But in case of NCFET, it is negative. The Dibble factor is
Dibble factor is nothing means it's a graph between GM2.
no, sir. This is why I have calculated this graph is this graph I have used to calculate threshold voltage at low drain bias.
At
Low drain bias.
low drain.
Just see the drain bias here is 0.09. Here the drain bias was 0.9. So I have used this graph to just calculate the value of threshold. So I got the value of threshold.
Okay.
And I got my Dibble factor as 0.0987 for MOSFET and these are the values for the NCFET. TFE equals to 5 nanometer and TFE equals to 10 nanometer.
Ultimately, the lower drain threshold means low power requirement.
No sir, actually drain induced barrier lowering, if it is going negative means it is very good for, means it is able to cancel the short channel effects.
Drain induced
Barrier lowering.
barrier.
Lowering. So means if value is positive means barrier is getting lower, but it is negative means there is actually drain induced barrier rising and it is good.
It is too fast. Drain induced barrier
Lowering.
lowering. Drain induced barrier lowering.
Lowering.
ठीक है.
So in MOSFET actually DIBL is there. But what is happening here? This is negative. The parameter is negative.
Yes.
So means actually drain induced barrier rising is there.
Yes.
So that will suppress the short channel effects in the MOSFET.
Okay. Okay.
So as how much time we have, sir? Otherwise, I'll skip a few slides redundant.
Only 15 minutes max.
So I'll skip the redundant slides in between and I'll directly go to circuit. So this is what I'll skip, and I'll go to this device analysis actually. So this part we have already discussed. This part was the NCFET, and I have designed one resistive load inverter using my device which I had discussed with you just few moments ago. And this is the VTC characteristic of this inverter. VTC means voltage transfer characteristic.
Okay.
So this is V in and this is V out. And if you see TFE equals to 0, this is the curve.
Yes.
For TFE equals to 5, it has gone more steep. It is coming down at very less voltage. And this is what is the advantage of having low subthreshold swing. For TFE equals to 10, it is coming gradually down. Not gradually, quickly. So this voltage amplification AG provided by ferroelectric oxide enables reduction in subthreshold swing of device, and the same is reflected in this characteristic. So whatever advantages which we got in our device, we are trying to see if from same device we are building some circuit, are we able to get those benefits or not. So this is like indirectly I have told that their subthreshold swing was low. So same has been reflected in this characteristic because it is sweep switching is there. Now this is one more thing which I have calculated is the noise margin.
Means immediately from high on current to low.
Yes, yes. Within very less voltage.
But 10 again everything is for 10.
Aslam sir, how much time we are having? Okay. So I'll try to finish off quickly. So this is dV out by V in versus V in. And through this characteristic, I have calculated VOH, VIL, VIL and VOH. So these are the table which I have got. And for TFE equals to 5 nanometer and 10 nanometer, if you calculate these parameters, it's more higher as compared to MOSFET. If you see here, NMH here is 0.58 and here is 0.689, and for MOSFET it was 0.44. So obviously this is higher. Similarly, low noise margin, here it's higher. In TFE equals to 5 nanometer, it's moderate, and TFE equals to 0, which is MOSFET, it is less. So noise margin is for this circuit is higher. Noise margin for the circuits designed with NCFET as a basic device is higher as compared to MOSFET. Now again, these are few characteristics like ID versus VIN. So like
Any ID versus
yeah, I'm coming on to it. So like here the voltage is falling. So obviously this current has to increase, the current in the device.
yes.
So this is again it is telling the steepness and the current is higher. Now there is one more term known as transconductance of the circuit. So transconductance also goes up. Why? Because the transconductance gets multiplied with transconductance of NCFET gets multiplied by AG. So transconductance for TFE equals to 10 is highest. The middle one is TFE equals to 5 and the least is TFE equals to 0. So this is what is mentioned over here. Voltage amplification AG provided by ferroelectric oxides enables us to get higher transconductance. And the most important thing is static power dissipation. So why this static power is going down is we have studied the IDVG characteristic in which we saw that off current of the device is TFE equals to 10, it is very less. We have seen it here.
Yes.
So if you see this TFE equals to 10 nanometer, the power dissipation is 0.1708 microwatts.
Okay.
For TFE equals to 5 nanometer, it is 0.2247 microwatts. And for TFE equals to 0, which is MOSFET, the power dissipation is 0.2 2983 microwatts. So power dissipation has gone down, and this is basically static power dissipation because we are judging the power at input equals to 0. So when input is 0, this is static power dissipation, and static power dissipation has come down drastically. So I can say static power dissipation for resistive load NCFET at TFE equals to 5 nanometer and 10 nanometer is 24.6 and 42.4% less as compared to resistive load MOSFET inward. And decrease in static power dissipation is primarily because the off current is going down, which I have discussed earlier in the slides. So there are few future
Is there
scopes.
anything about the dynamic characteristics?
Dynamic I have done, sir, but I have not included for today's talk. Dynamic I have not included. I have done a few things in dynamic response. So these are the future scopes. One is the absolute voltage amplification. What do I mean by absolute voltage amplification is? I'll just go back and try to explain. This is the amplification characteristic. So it's going like, it's behaving as a non-linear, and which is basically because the capacitance, ferroelectric capacitance has non-linear nature in itself. Because if you see just the characteristic VF equals to alpha QF QD 3, non-linear is there. So that's why this non-linearity is there. We are not able to get absolute value of amplification or in the device. So there are two ferroelectric materials which are known as second order and first order. So at present whatever I have showed you is a second order ferroelectric material, and there is one more material which is known as first order ferroelectric material. In that alpha and beta both are negative. Like here alpha was negative, beta was positive. In that material alpha and beta both are negative. So what we will be trying to cascade that two ferroelectric material, which will lead to cancellation of anisotropic constants, alpha, beta. If we are able to suppress these non-linear terms, then we will be in a position to get absolute voltage amplification. One was this, and this is what I have written over here. Second is scaling of ferroelectric below 10 nanometers. Like I told, we started with lead zirconium titanate, which has ferroelectric thickness in hundreds of nanometer range. BaTiO3 barium titanate, it also has the thickness, critical thickness around 300 200 nanometers. And from that we have gone for doped HFO2, which has critical thickness of 10 nanometer. And here undoped HFO2 critical thickness is 10 nanometer. So if we are able to scale it further below in 1 or 2 nanometer, it would be great advantage for us. And one more thing which I wanted we can focus on is digital and analog circuit design using NCFET. As I told that Dibble, because of Dibble drain induced barrier lowering, barrier is actually not lowering, it is rising. So it is good for circuit application. So I have a plan of.
You will reduce the short channel effect.
Yes, short channel effect.
Sir, your previous 1 to 8 slide, just please explain.
Yeah, no problem, sir.
Your 1 to 8 slide.
Yeah, it's here, sir. It is here only, sir. It's in the.
Yes, over there.
Acha, you have to see. Okay, no problem. Most of the slides are from previous lecture only.
Okay, but even then.
Yeah. So this is the first slide. Second slide. This is the same slide which I used. And this is also, I think we had discussed. This is a new slide. There are many mechanisms, many kind of research is going on. SY, double gate, FinFET, tri-gate, gate all around.
Yeah, it is new for me.
Yeah. So it's like why there is a short channel effect. The main reason is the gate is losing control over the channel. We are reducing the channel length in order to make our device compact. Like if we go 10 years back, 10 or 15 years back, the size of pen drive was, it used to be a big pen drive. Now it is, I'm having 1 TB space is there in the mobile itself. So we are going towards the miniaturization.
Yes.
But in that process, what is happening? The short channel effects are rising. So somehow we have to develop the mechanism to reduce the short channel effects. So these are the architectures through which we can reduce the short channel effects.
Extremely thin SOI, double gate.
Double gate. So means gate is at both sides.
FinFET, tri-gate,
tri-gate,
pi gate.
pi gate, omega gate, gate all around, gate is everywhere.
And your topic is NC-FET.
Huh. So this is for control of gate over the channel.
Yes, okay.
But NC-FET what it does is it reduces the subthreshold swing.
Yes, yes.
And this is the slide I think I had.
Okay, yes.
This slide is also same from top one.
Yes.
And this was, I think,
Page space for MOSFET. If
This-
sir-
this is what, sir, actually I told, Aslam sir, do we have time?
Yes, yes, go ahead.
So I told that subthreshold swing is a combination of two factor, body factor and transport factor. So if subthreshold swing has to be reduced, either of them has to be altered. So here I have taken transport factor, here I have taken body factor. So actually there can be four possibilities. Like two terms are there, the four possibilities of reducing. One is M is greater than 1, means body factor is greater than 1, and N is less than 60.
Okay.
So means what? Body factor remains the same. I am changing the transport factor.
Okay.
So like in MOSFET what happens, there is a drift diffusion phenomenon. The carriers which are moving from source to drain, they travel by a mechanism known as drift diffusion. So in that there is a limitation of 60 millivolt per decade. But here the transport factor is what? I have changed the transport factor. On TFET, IMOS, all these kind of devices that comes under this category. There the transport is something else. There is a tunneling. The charge carrier tunnels from source to drain.
Yes.
So this is one category. Now this Boltzmann FET. Boltzmann FET means our MOSFET only. M is greater than 1, means 1 plus C depletion by C
Okay,
oxide.
N equal to 60.
Yes, and this is 60. Now this is Landau FETs. Landau FETs in which I am working. I am working, what I am doing? My transport is same. I haven't changed MOSFET.
Yes.
Transport is still drift diffusion. The carriers are moving from source to drain and the current is flowing.
Yes.
What I have done? I have altered the body factor. So
M.
this I have altered. I have made M less than 1. Transport remains the same. So this is Landau FET. Under this 3-4 things comes. One is NC FET, one is suspended gate FET, one is negative capacitance phase transition FET, hyper FET, and there is super FET. Super FET means what? I am altering both transport factor and body factor. Suppose in my this only, I'll just show. Instead of having MOSFET, I have here TFET. So in TFET, transport is changed and body factor is already changed. So both body and transport factor are changed. So this comes under this super FET category,
Okay.
where both transport factor and body factor is changed. So here subthreshold slope will be, swing will be very
But
less.
in case of tunnel FET, you are changing the transport phenomena.
Yes, correct.
क्या research उसमें हो रही है transport phenomena?
Sir, the first article in TFET came in 2007. First article which I saw was Kethi Bokart in 2007. So actually Aslam sir work is also in TFET.
Okay.
Aslam sir has worked in this area, I have worked in this area.
Okay, okay.
And maybe someone can take this also. Some work is still going on this area. Super FET, where the people are altering the transport as well as body factor. Suppose that is what I am telling. If we design NCT FET, negative capacitance also and TFET also.
Yes.
So that comes under this category and super FET, in which both are changed.
Everything is
So I hope I was able to convey the things to you. Thank you very much.
Thank you, sir, for such a nice session. Now I would like to invite Prakash Saxena, sir, to present memento and the FDP kit to our guest.
रख दीजिए, एक मिनट अभी फोटो ले जाना है।
Thank you, sir. Now this is the end of the session.
Hello, thank you, Dr. Avadia, for such a nice session. Both of your sessions, they are really interesting, and as a keen listener, I really like your efforts to handle me.
Thank you so much, sir, for your kind words. It was very nice interacting with you. Thank you so much.